Hello, everybody, and welcome to the Cosmos Show, the place to be if you're curious about the universe. I'm your host, Dr. Sam, the founder and executive director of Wyoming Stargazing. Here, you can pick the brains of astrophysicists, get advice from a space doctor, learn all about life from astronomers, and find out what's going on above your head, all in the same place. Join us live every Tuesday, 6 p.m. Mountain Time. Every other Tuesday, that is, 6 p.m. Mountain Time, on YouTube and on Twitch. Remember, you can chat your questions on Twitch and YouTube, and you can also call in and ask your questions. We would love to hear from you. The number to call in and the ID that you'll need to do that is up on the left-hand corner of your screen. So please give us a call. We would love to hear from you. Today's show, we are going to be talking about black holes, gravity, and wormholes. And here to tell us all about those wonders of the universe are not one, not two, but three special guests. We've got the president of the University of Wyoming, Dr. Ed Seidel. We have professor of mathematics in physics, Dr. Gabrielle Allen, and we have professor of physics, Miguel Alcubierre, who, among other things, has designed what one day might become the first real warp drive. So stick around for the special guest segment. But before we get to that, let's introduce our co-stars. First, we have postdoctoral fellow from the Simons Observatory. It's Nick Galitsky.
Hi, Sam.
Hey, Nick. Thanks for being here. And next, we have the Deputy Director of Education and Outreach from the Vera Rubin Observatory. It's Dr. Lauren Corlees.
Hello.
Hey, Lauren. And we're going to have Dr. Danny join us in a little bit. And unfortunately, Nora Bailey isn't going to be able to join us this evening, but we'll have her back in a couple weeks. Tonight, it is Nick's turn to tell us a little bit about what he's been up to and what's going on at the Simons Observatory. So Nick, we are all yours.
All right, fantastic. So yeah, kind of keeping up to date with what I'm working on. If you go to that first slide, is talking about the telescope I've been working on, which I've talked a bit about before. There it is, affectionately named B-Rock after the CM Beastie Boys. And we have a little fun in the lab. I got to name some things. I like musical themes personally. And this is you're looking at a CMB, cosmic microwave background camera, effectively, and it cools down detectors down to 100 millikelvin, really cold. And we go stare at the, basically a chunk of the sky for about 5 years to get a few numbers that tell us about the first few fractions of a second of the universe. So that's a really awesome science case, and it's worth reading a whole lot about. But I'm talking more about the experimental side of what's it look like in the lab. And especially since I've spent the last few years designing and building and procuring parts for and coordinating all manner of things to make this camera come into existence. And to kind of answer the direct question of what am I working on right now, what I'm working on right now is mostly writing the paper about the last few years of the assembly and testing of this instrument to show, hey, we've built a really cool camera here, and it's going to do some amazing things. And let me tell you, how we know it's going to do amazing things, how it's meeting our objectives to deliver the science we'd like to see. So to talk a little bit about kind of what's gone into it, it's kind of a wild ride, and it's been quite a journey to get this camera to where it is now. So go to the next slide. One of the cool things about these types of telescopes is there's few places in the world that have all of the expertise to bring it together. And so we end up bringing parts in from all over. So our first stop is actually in Italy. And that's actually a picture of me with my colleague Amir, and the two of us designed most of it. Hanging out, and you can actually see that's the aluminum shell, vacuum shell being welded together in Chivasso, Italy. We got to go visit a couple times to make sure manufacturing was going well, of course. And then that was shipped to us almost a little over 2 years ago, summer 2019. And there at top right, you can see the big old box it came in. And me with a big grin on my face when we first unboxed it. Always, good. I know I hear unboxing is really popular on online these days, so that's a good one. All right, next slide. So then we got to start putting it together, and I'm calling out this specific piece from New York because this is one of the most important pieces. This is from Syracuse. There's a company there called Cryomech that makes pulse tubes, and pulse tubes are this fantastic piece of technology that kind of uses a trick of pressure gradients in physics to pull heat out of objects. And so, as I mentioned, this needs to be cold. This is the first things that gets us cold. And looking at that piece on the left, the very top of it and the very left sticks out of the side of the vacuum shell. That middle kind of copper ring is at 40 Kelvin or somewhere negative 300 something Fahrenheit. And then the gold plated part on the very right there goes down to 4 Kelvin, or about negative 450 Fahrenheit. And it can cool a fairly large volume, as shown by a graduate student there, Ashrita, who's hanging out inside the camera, assembling and attaching our temperature stages to this. And so that's the first thing to note about this camera is it's got a bunch of layers, 2 principal layers to shield us from the very hot lab environment and keep things cold inside. All right, going to the next slide. Continuing on that trend of expensive things to get us cold is all the way from Finland. Unfortunately, I haven't got to travel to Finland to go see this company, Blue Force. Well, we would love to someday, and they are a handful of companies in the world that build these units called dilution refrigerators. Now you've got 4 temperature stages, which you can kind of see on the left there. There's 4 levels of the cake. The top level is that same 40 Kelvin layer. The next layer down is 4 Kelvin. Then you get colder, next layer 1 Kelvin above the absolute 0. And then the very bottom stage there, I've actually seen this with my own eyes, is they can cool that down to 7 millikelvin, or 0.007 degrees above absolute 0. We operate the camera a little hotter than that, around 100 millikelvin, but still very cold. And that's about negative 460 Fahrenheit for those in there. And so that got delivered to us, San Diego from Finland. And you can see us installing it in the camera on the right there with a graduate or an undergraduate researcher we had working with us. And another fantastic opportunity to take a great selfie in the gold-plated protective shell around the cold stages there. All right, moving on. Now we're kind of slowly building it up. That's our cryogenic infrastructure. Let's go next slide. And this is going into from Wales. This is actually kind of interesting. I work very closely with this research group in the University of Cardiff, and they are the one place in the world that can make these filters. And so for the astronomers on here, we use filters to reject light from outside of the wavelengths that we want to look at. It's a little more important for us though, because in order to keep the camera cool, you have to basically get rid of all the infrared, because that's a lot of heat transfer as well. So these are very specialized filters that reject the infrared radiation, but let in the millimeter wavelengths that we look at. And these are big. These are almost, these are 60, 70 centimeters in diameter for the telescope. And you can see it installed in the telescope on the right, as well as just a very nice shot down at the window of the camera from above, where actually the group in Wales also makes our windows. All right, let's go to the next slide here. So we're doing a pretty good international trip so far. But that's not all. We also bring in parts from Japan. And in fact, this is more less of a company, and actually Cardiff University, those are collaborators. The difference, a company, you send them a request and you pay them some money and they deliver the component and they tell you it works to spec. A lot of these are so custom that it's an entire research group dedicated to making them. And that's true of what I'm showing here, which is basically our optics. And what's super, super cool is that top left image shows our entire optics tube assembly, which is an assembly of 3 lenses. Each lens is about 40 something centimeters in diameter, made out of a single crystal of silicon. And I think they're a few centimeters thick. So I think each lens weighs about 10 kilograms or something like that, 30 pounds. So they're pretty hefty pieces of equipment that we got to put in there and assemble in there and keep rigid, right? So they're all aligned properly. In this whole process, we do that. And the lenses make quite the journey, because I think they're actually, the silicon's manufactured in, I want to say Japan, then it's shipped to Chicago for grinding and the application of the anti-reflective coating, and then it goes back to Japan for assembly into the optics tube as a unit, and then that comes back to San Diego where we install it in the telescope, which you can see top right there. Japan also makes a really cool device called our half-wave plate rotator. And I think a lot of us physics nerds on here love looking at these demos or actually playing with them. We have a setup at San Diego where you cool a puck of a ceramic, a high temperature superconductor, and then you can levitate it on a magnetic track and push it around the track and it zips around. There's great YouTube videos of this if you want to look at it. Superconducting levitating track. And the material is called yttrium barium copper oxide, YBCO. And what you see in that bottom left image, all those little rings there, those are a bunch of YBCO pucks that perform a superconducting magnetic levitation bearing. And so it doesn't work until you're cold, but that's that 40 Kelvin stage. We cool down and it levitates this like 50-pound optical device above the first lens that spins around at 2 hertz. And the whole idea is to modulate our signal. If you have a modulated signal, then you can pick that off and ignore anything that's not modulated, that's not the signal you're trying to look at. For those people on here that are really the optics nerds among us, it's a half-wave plates. We actually rotate our polarized light signal so we can pick that off more easily and ignore anything that's not linear polarized light. And there on the right, what?
Can you please say the name of that superconducting material 10 times fast, please?
No, I cannot. Good challenge. That's why we call it YBCO. I can say YBCO as fast as you want. And then on the right there, you can see us install the track and then also the device that sits on top of it, a kind of temporary device actually to test it. Going on to the next slide, then it gets a little closer to home for the rest of it. But that's not to say there aren't a lot of different components coming in from the US. This is kind of really attesting to the fact that the Simons Observatory is a collaboration of 300 people scattered all over the world with various specialities. But the top left is our electronics from the Bay Area. And below that is the wiring harness to get wires in from 300 Kelvin to 100 millikelvin is a little challenging. So that's actually the middle left image, the bottom left image, and then the bottom middle image are all the wiring to get just our signal from the detectors from that 100 millikelvin cold stage out to our 300 Kelvin stage. And then the hexagon is probably one of the cooler parts because that's our actual detectors. That's where the light goes in and is absorbed and converted into a signal we can put on a computer. That's coming, it's one part made in Boulder, one part made in Virginia. Those go to Princeton. Princeton does the assembly and then it comes to San Diego. And then we put it all together and we get a camera. And that's me looking really excited over there because it's finally all coming together. And we've been testing that wafer that I'm showing the picture of for the last 4 months. And that was the last piece we needed to start writing a paper about it. So you go to the next slide. So what am I doing now? I've spent the last 3+ years designing, integrating, and testing this device. We now have enough components in it to say, yes, we have a camera. I can talk about how well that camera has performed. Hilariously, we've done so much that I can't actually include the optical performance because that's too much. That's going to be a whole nother paper. This is just the performance of the cryogenic, the cold stages, the detectors, all that. Spent the last 3 years doing it. I've spent about 6 months now writing this up for people who do scientific writing. That symbol there is the overleaf symbol, which is basically the Google Docs of the science world. And it's a LaTeX compiler, which is effectively a programming language for typesetting, which is great fun once you get to know how to use it. And then hopefully we're almost to the stage where we're at a draft that we can send around for review. And then we get into the review process, which 6 months is maybe how long it will take is we're a big collaboration. So first you get the review and the collaboration, and then we submit it to a journal, and then we get the review from the journal, and we'll probably have to fix some things and resubmit it at least once. And so that will go back and that'll take us a few months out in the future. And that meme is the classic reviewer number 2, always got to be so hard, always got to be so harsh on us and make us work harder to get a publication out. But that's, yeah, so that's what I'm working on right now.
That is super cool, Nick. And congratulations. It sounds like you guys have hit a major milestone in your work for several years. So
yeah, no, it's fantastic. It's great to see it all come together, and it's a really, really beautiful instrument. I'm really quite proud of it.
Very cool. I'm going to be relocating in California pretty soon here in the Bay Area, but I'm definitely going to make a trip down south, and I'd love to take a peek.
Of course, we're all happy to give out as many tours as we can. Yeah.
Sweet. I'll be there.
I wanted to ask, like, how did you first get the idea for this camera? Was it like this thing that sort of came to you one day, or was it like sometimes that happens? You like get this inspiration. You're like, oh, I've never thought of it that way before. Or sometimes it's like, I've been slowly building this in my mind, and now it's this coherent thing.
It was just like J.K. Rowling and Harry Potter. He came like fully formed in Nick's mind. He saw the whole camera at once.
There you go. Yeah, I looked at Canon DSLR, and I was like, well, that's a pretty good idea. No, so this is let's see here. How do we do this? It's taken years, I'd say, of background knowledge and people playing with what works and what doesn't to get to where we are. And so I'd say that's kind of the background here. Is where I started, was reading the literature, looking at what everyone had done before, what had worked, and some of what had not worked. There's plenty of that as well. And I'd say all of it's really kind of built around our detectors, and our detectors are called transition edge sensors, which are a cool device that's just a fancy way of saying they're a superconductor. And if you can basically balance your detectors between the superconducting state and just between being a resistor effectively. And when they're finally balanced on that transitioning edge, small changes in the power incident on that detector cause rapid changes in their resistance. And so by looking at, basically we do a conversion of the resistance to a signal about the number of photons being absorbed, or the amplitude of the photons being absorbed. And so that's the kind of principal technology. And the reason why is because that is the most sensitive detector technology. I would say that's been, God, they've been doing these variations on millimeter detectors for 30 years, and that's the one that rose to the top. We do see some new technologies and how to read them out and that sort of thing, but that's really what you base it around, because those detectors are superconductors that superconduct at around 160 millikelvin is their transitioning temperature. And so that means we have to be that cold for them to work. And that's kind of where it started. And then you looked at a bunch of different designs. And I'd say early in this process, it was me and Fred were hanging out a lot. And Fred designed the optics, and he'd give me an optics design. I'd tell him whether I could cool it down or not. And eventually we ended up with just essentially like a Canon camera, a bunch of lenses in front of a camera, and some cryogenics shoved in off to the side. And then there's some iterations on that. And, frankly speaking, if you look at this design, you look at the last 10 years of cosmic microwave background telescope designs, there's more than a few similarities. We definitely borrowed heavily from our predecessors. So happy to say that. But I was excited when we finally got this design and squared away, and we're happy with the optics and happy with the cooling and that sort of thing. And then then it took a few years with some modifications in between.
But to me, that's always one of the fun things, when you can take a bunch of different existing technology and use it in a slightly new way, and then you get to make all of these new discoveries. And that, I don't know, I find that kind of process, that tweaking, super clever and really interesting.
Yeah, no, it's a lot of the fun of being an experimentalist.
Yeah.
Nick, for the benefit of folks who might not know what absolute zero means, can you say a little bit about what that is?
Yeah, I mean, temperature is a funny thing, right? And I spent a lot of time thinking about it. And it's the basic principle of the Kelvin scale versus Celsius or Fahrenheit is ultimately temperature is a measure of how much energy is contained within a material or an atom or something like that. And that's kind of the way to think about it, is kind of an atom or molecule bouncing around a little bit, right? So it's the energy contained within there. And absolute zero is just to say there's no energy in that anymore. You've extracted all energy from this. It's absolutely still. And that's very hard to do. And there's actually people that there's a whole branch of physics that is focused on getting to colder and colder temperatures to understand the properties of materials and atoms and that sort of thing. And they can, it gets far more advanced, where you're basically trapping single atoms in laser traps and low energy wells and that sort of thing. That's very cool. We don't have to do that, so in that sense our temperatures are warm, but by reducing the amount of energy out of it, this is, that's getting into the Kelvin scale. That's what absolute zero is you've removed all the energy, and it's very hard to find. Even space is warmer than that, right? The CMB itself, which is photons buzzing around everywhere. And this is kind of a funny thing of working in this field, is I see the world in temperatures. And so it's like space is 3 Kelvin because of the CMB, but actually you got stars and dust and that sort of thing. And all the dust and gas in the galaxy is around 20 Kelvin. So really about as cold as you get is 20 Kelvin. There's a fun paper a few years ago, I think from a dark matter experiment, where they'd cooled a volume like a cubic meter or something down to below a Kelvin or something like that. And they did this fun paper where they figured it was probably the coldest cubic meter known in the universe. Because most of the universe, I mean, there's cold spots. Space is cold, but it's not that cold. You have to actively try to get below like 20 Kelvin or 3 Kelvin, depending where you are in space. So that's kind of a fun thing about it. Yeah, and then, of course, the room's 300 Kelvin. We're pretty hot around here. And this all factors into our telescope, that anything that's hot, room temperature, is bright to us, because not only does thermal properties tell you how much energy is in a material, but it also tells you that how much energy it's radiating out. And that's like the sun is as bright as it is because it's 5,000 or 6,000 Kelvin, right? Infrared cameras work because we're hotter than the, room around us. We're at 300 Kelvin, everything else is at 280 Kelvin or what have you. And so these are all just kind of differences when you think about the Kelvin scale, which is obviously the scientific side reference versus the much more practical Celsius and Fahrenheit for humans.
That was a great explanation. Thanks, Nick. I appreciate that.
Yeah, no, it's a great question.
Yeah, and yeah, thanks so much for your presentation. That was awesome. And I love the fact that this camera is coming together from so many different people from so many different countries all over the world.
Yeah, it's a big group effort. That's the heart of a collaboration, is getting all those pieces to come together well and build something beautiful.
Yeah, that's super cool. Well, let's move along to astro advice, life advice from astronomers. And just after that, we'll bring on our special guests. So tonight, since we're talking about black holes and gravity, cosmic microwave background radiation, we decided to include a quotation from a recent Nobel laureate, Dr. Andrea Ghez, who was honored for her contributions towards the discovery that supermassive black holes lie at the center of almost every galaxy in the universe. And so she tells us that the question that I started off with was, I thought, very simple. It was just, is there a supermassive black hole at the center of the Milky Way? But one of the things I love about science is that you always end up with new questions. And for her was that was, are there supermassive black holes in the center of every galaxy in the universe? And it turns out that that there are. So I think that's pretty fascinating about the way science works. Nick, you talked a little bit about that, about how the design changed as things were going, and you learned a lot more throughout the process. And Lauren, I know you study galaxies, and so you probably have a lot of experience in how questions can change over time as well. So yeah, if anybody has any comments they want to make about Dr. Gez's quotation, we can chat about that for a few minutes, and then we'll bring on our special guests.
I was going to say, I love it because, yeah, a lot of, that whole camera and everything I just talked about is motivated by one question, which is, what happened in the first fraction of a second of the universe? That's, you start very simple and kind of go from there. I say there's another good question I like that this reminded me of that drives another part of my research, which I'll talk about someday, which is, where do magnetic fields come from, especially like galactic magnetic fields or intergalactic magnetic fields? It seems simple, but as soon as you start diving into it, it's like, wow, that takes you all the way back.
Yeah, same. For my research, it's more along the lines of like, how do galaxies form? You're like, well, that's a really big question. We should not know the answer to that. And it's interesting when you start to ask those questions, there's always sort of an answer, right? Like, how do stars form? Well, gas collapses and forms a star. And you're like, okay, well, where did the gas come from? How did it actually collapse? What is it made of? And you can just suddenly, you can take the simple answer. And if you just continue to be curious and ask more questions, you'll realize that like, oh, we don't know. We don't know most things really, which is kind of fun contrast to make to like how textbooks and things present science of like, we have all the answers since the 1700s. It's like, no, we don't really know anything at all.
Yeah, that just, oh, go ahead, Danny. And welcome, by the way. Thanks for joining us.
Absolutely. Thank you for having me. So one of the things that they tell us in medical school is that about 50% of what we learn in the 4 years that we're in school is going to be wrong. We just don't know which 50%. And so that's, you know, I think that is exactly along the same lines of what Andrea is talking about here. So, you know, new questions, certainly the more we learn about medicine specifically, the more questions arise and the more we realize we really don't know. So that's something that I find exciting. I think a lot of the folks on this call probably find exciting too. But yeah, that's what makes us scientists, you know?
Yeah, there definitely seems to be something pretty basic human about being curious and following questions out to their logical conclusions. And that's probably a great segue here into our special guest segment, because really what black holes and wormholes and warp drives all have in common, among other things, is Albert Einstein, who followed some very simple questions out to their logical conclusions. So we're going to take a quick 30-second break. Then we're going to come back with, like I said, not one, not two, but 3 special guests. Stay tuned. It's going to be a lot of fun. We'll see you in just a second. Bye. Hello, everybody. We're back on the Cosmos Show with our 3 special guests tonight to talk about black holes, gravity, and warp drives. President Seidel, Dr. Allens, and Dr. Alcubierre, thanks so much for joining us.
Hello, thank you for having us.
Yeah, it's a pleasure. So I know you've got some slides prepared to kind of set the groundwork for everything you're going to be talking about. I'd like to ask all our special guests to answer one simple question throughout their presentations, which is, what's the one question that nobody asks you that you wish somebody would? And you can start with that. You can put it off to the end of your presentation, whatever you like. But yeah, at some point, I'd love to hear what that one question is from each of you. But I'll turn over to the 3 of you, and you can take it away.
I have an answer, which is, nobody asked me, how do you get paid for having so much fun when you're doing science? And so I remember as a grad student with my fellow grad students just marveling at the fact that I was getting paid $450 a month to do science. I couldn't believe it. It was really great. And even today, I've somehow gotten out of doing science most of the time, but the most fun I still have is doing stuff like this, talking about it at least.
That's awesome. Same here. Dr. Alcubierre or Dr. Allen, you want to respond to that question before we get into the slides, or do you want to hold off for a little bit?
I'm going to hold off and think about it.
All right.
Yeah, if you want, I can answer also. Well, I can answer first the other way around. And what's the question everybody always asks, and sometimes a bit tiring, and it's precisely about what I'm going to talk about. Is the warp drive.
Oh, I'm sorry. It's so cool.
Yeah, but the one question nobody asks. It's very similar to what I just said. Is what is it that I actually like to do when I'm doing science? What are the things I like? Nobody asks that. And well, the answer is that what I like to do is I like to write. I like to write papers. I like to write articles. I'm currently writing a textbook, so that's the things I like to do. And I like a lot to code. I do numerical relativity, which means I do a lot of computer code, and I really enjoy coding. I mean, I find it extremely fun, and I can spend hours doing that, and time just goes by. So those are the things nobody asks, but those are the things I really like.
That's awesome. Thanks for sharing. All right. Well, whenever you're ready to start sharing some of this cool information with us, please go ahead.
Okay. Well, Samuel, I'll start off. And so we have a planned program here. So I'm going to talk for a few minutes about basically the history of numerical relativity and gravitational wave discovery, and starting with Albert Einstein himself. And then Gabrielle's going to talk about kind of current best practice in actually solving Einstein's equations and trying to identify the signals, including using artificial intelligence and advanced technologies. And then Miguel's going to take it a little further into the future about the very advanced potential future of what might have to do with general relativity. So if it's okay, I'll dive in. So the first slide here just sort of previews this, but the thing I really want to point out is that the three of us had an incredible amount of fun working together as we started at the very early Albert Einstein Institute, or Max Planck Institute for Gravitational Physics in Potsdam, Germany. And we just gave it everything we had for years, and it was really so much fun. And that's why we're still very close friends and work together whenever we can. So the next slide, I just want to dive in a little bit to Einstein himself. And I want to point out that what we're going to be talking about tonight is not what some people think of Einstein for his work, the so-called miracle year of 1905, when he wrote these 4 papers that laid basically all the foundations for modern physics, including E = mc squared and the foundations of quantum mechanics. After he did that, he thought really hard for 10 years before he came up with a more satisfactory theory that he thought would be necessary, which included gravity, and that was his famous general theory of relativity. And that is the theory that has really set the foundation for all we know about modern cosmology and now gravitational waves and so on. I want to point out one thing. He worked with his wife, Mileva, and some of you should, if you haven't seen the National Geographic series on Einstein, it has, I think it's an 8-part series on the history. And she was the smart one. He was the dreamer. And when he got stuck, she helped him, and she never was credited in any of his papers for her work. And so I just wanted to point that out. That's sort of, at least historically, now seen to be the case. So let's go to the next slide. So the next slide is just a very simple slide. It's my favorite equation of all. It's, to me, just the way it's typeset is beautiful. It's general relativity, and in the famous Wheeler, John Archibald Wheeler, who was a very famous scientist who coined the term black hole, had this pithy way of saying that the left-hand side of that says that space tells matter how to move, and the right-hand side says matter tells space how to curve. And that is the beauty of Einstein's theory. It's the geometric theory of gravity. And it's, as Einstein said, a theory should be as simple as possible, but no simpler. And it comes from extremely simple ideas. But the trouble is that the equations, when you write them out in their full form, are almost impossible to solve. Einstein himself was unable to solve them except in special cases. The entire mathematical physics community for a century struggled, has had various solutions, but eventually people turned to computers to solve them, and I'll come into that in a minute. So the next slide, please. So in spite of what I just said, within 1 year of publishing those equations, 2 of the most important predictions of those equations were realized. The first by, I don't know which came first, but Einstein himself said, what happens if you have a tiny perturbation, something's not exactly flat space-time, but very weak gravity? And he discovered these wave-like solutions, which were later known to be physical effects, but were quite controversial for a long time. But anyway, those are the so-called gravitational wave solutions that people puzzled over. What are these? Are they merely coordinate effects, or are they real physics and so on? And at about the same time, Carl Schwarzschild came up with the spherically symmetric time-independent solution, the static solution, the simplest sort of physical solution that is represents a black hole. However, it was at the time known as the Schwarzschild singularity. No one really understood what it meant for many, many years. And the term black hole for that wasn't coined until the 1960s. So the point is that there were a lot of things going on and people weren't really sure what they meant. In fact, the next slide shows Einstein himself. First of all, he never believed that even if gravitational waves were real, that they could ever be detected, because they would be so weak that he could think of no technology that could possibly detect them. But then even something like 20 years after his initial paper proposing that there were gravitational waves, he wrote a paper trying to retract his prediction. And incredibly, someone had the courage to reject his paper as being wrong. And then he himself recanted on his retraction and said, okay, well, maybe they're real after all. But it wasn't really known until around 1960 that you could prove mathematically that if gravitational waves are leaving a localized source, that the mass of that source goes down. And so then it's really clear, it's a physical effect. And so then the race was on to see if you could ever detect these gravitational waves. Next slide. So yeah, so then the next thing just says, Einstein here is at a blackboard trying to figure out what on earth his equations are telling him. And on the right-hand side, I have a picture of like one page of hundreds of pages of the equations written out in their full partial differential form. And so basically no one is able to solve those in their full generality. So the race is on then to see, could you use computers in order to find numerical solutions to these equations? So next slide. So I would say it's a kind of a miracle that over an entire century, from 1915, 1916 to the year 2016, the technologies, both of the supercomputing side and the mathematical algorithms that are needed to solve them, finally came together, and we're able to solve Einstein's equations and predict, say, what would happen if two black holes were to collide. Not just one black hole, but according to the theory, you get these gravitational waves. If I just do this, I'm actually emitting waves. But the only things that might be enough energy with gravitational effects to send out detectable signals would be things like black holes multiple times the mass of the sun colliding at near the speed of light, or neutron stars and such things. So the techniques to actually solve those equations were developed over decades. And I have a picture on the left here of a guy named Larry Smarr, who pioneered this field and standing in front of the so-called Blue Water supercomputer at the University of Illinois, a $200 million supercomputer, just one supercomputer, just for the hardware. So Larry's PhD thesis in 1975 was the collision of two black holes. For the simplest possible case, he did very advanced work at the time, but we wanted to see what happens if two black holes are going around each other, or neutron stars. And it was a struggle for the entire community for about 30 years, until around 2005, when the techniques had advanced enough to do it. At the same time, on the right-hand side, I show a picture of the gravitational wave detector supported by the National Science Foundation that became operational in the early teens, really, the advanced LIGO detectors. And then lo and behold, next slide, in September of 2015, basically they turned on the upgraded detectors, and before they were even finished calibrating them, they saw something. And it's like, oh my gosh, we actually saw something. And then it turned out that the signals look exactly like what our numerical simulations have been saying for decades. And so it was, I practically cried when I saw it. It was just like exactly what we were talking about. And so this is a picture that was taken. That's Gabriela Gonzalez, who's a professor at LSU, and that's Kip Thorne, one of our three mentors. I mean, the three of us all sort of looked to Kip as one of our mentors. And that's a picture in the day that those the gravitational wave discoveries were announced. So I'll go to the next slide, and then it's going to be up to Gabrielle to take it from there. So the idea is that we have, the next slide gets into just the fact that not just one detection, but multiple detections, including multiple black holes colliding in different binary pairs, and then neutron stars and neutron star black holes. And so you start to then coordinate. If you just press one more advance, there you go. All of those New York Times, the front pages of every science news and the Champaign News Gazette, it's everywhere, the excitement on all of this. And so you begin to think about not just gravitational waves, but how do you correlate that with electromagnetic waves, and like with regular telescopes or advanced telescopes like the Vera Rubin Observatory, and neutrinos. And that's what multi-messenger astronomy is about. So I'm going to pass it on to Gabrielle to talk about current modern day practice of the best of those kinds of simulations to detect those waves.
Thanks, Ed. So next slide, please. So as Ed mentioned, the future of astronomy now is going to be all about multi-messenger astrophysics. And this really means that we want to be able to observe these different events like supernova or colliding neutron stars using different messengers, whether it's gravitational waves, light, neutrinos, or cosmic rays. And so when we can get all this information at the same time and compare it to our numerical models, this is going to help us find new discoveries and insights about the universe. So next slide. So the question then is, how are we going to model these multi-messenger objects in the universe? And so what we've been doing is using a code base, a community code base called the Einstein Toolkit. And all three of us have a long history with this. It really came out of the Albert Einstein Institute in Germany. It's now supported by the National Science Foundation here. And the way this toolkit works is it lets you divide up a complicated modeling problem into smaller parts. So that then each part of the code is typically a graduate student project, or an undergraduate student project. I think the clever stuff is how you can put these different pieces together so that they all work to solve a complicated problem like a neutron star collision. And you know, that's part of the kind of the computer science part of this this project. But now it's also a community code. It's an open code. It means anybody can take the code and use it for whatever they like. But there are hundreds of these code components that you can put together. You can form a complete model of a black hole collision or a neutron star collision or a supernova. And we have a small core team that works to support the toolkit and to steer the development of the code so that it works. We have over 300 users of this now around the world, which I think is pretty cool because the black hole modeling community is not so big. And we have a help desk and weekly meetings, summer schools and other mechanisms. And I think that the really great thing I think here is that it allows new users to get started with modeling and get started with relativistic astrophysics, whatever size a group they are. Next slide, sorry. As you put it here, it also provides a way, because it's component based, as soon as there's new science or new algorithms or new computing technologies, these different components get upgraded or get extended to, and it means that we can always add new features and new components and make sure that it runs on modern computers easily. So next slide. Talking about computers, typically these models are run on supercomputers, you know, for weeks at a time. So they're rather expensive to run. The machine on the left is Blue Waters, the supercomputer that we were using in our group with Ed at the University of Illinois. Now in Wyoming, we're very lucky to have the Cheyenne supercomputer at the NCAR Wyoming Supercomputer Center over the mountain here, just in Cheyenne. And so we're just getting going on that resource. But the way the code works is that once somebody has ported it to a new machine, that's automatically available to the rest of the community to use. Next slide. If you could just press play on that, this should start running. So this is just an example. This is a simulation that a student of ours in the Illinois group, Sean Rosowski, ran with the Einstein Toolkit right as the first gravitational wave discovery was made. And this kind of just shows in the middle, you can see the two black holes slowly spiraling together and the gravitational waves that are being emitted here. If you can just advance through that and go to the next slide. I think the really cool thing here is that, you know, now this has been done, anyone can actually run this now. You can go to the Einstein Toolkit webpage and download the parameter file, download the software, run it on a computer if you can find one with a few cores. Or you can skip running the simulation and you can just play with the data. So other members of the community have posted all of the data for this up on an open data repository. And so you can get complete codes and get going on working on this kind of modeling. Next slide. The other part of the problem, if we want to do multi-messenger astronomy, is how we're going to find the gravitational wave signal in the noisy detector data. And on the image here, there are four the signals on the red signals of the time series data from the detector. On the right, you can see the signal in the frequency domain. If you just look at that, it's very hard, impossible, let's say, to figure out, is there a signal there? This is the noise from all the different noise sources in the detector. If you look carefully, you can see we've sort of embedded the signals in there, but you wouldn't be able to see those without having fancy tools to get them out. The community has been building up software for a long time in preparation for these discoveries, and as a typical method of finding signals with match filtering. One of the other things that's going on now is looking at how to use new data science technologies and approaches to do this in quicker and to get more out of the signal. If you go to the next slide. Something else that we were doing in the group in Illinois now here is looking at using AI and deep learning to do this, to find the signal. And this really uses the same kind of methods that we routinely use on our, with our photo libraries now to identify images here, dogs and cats and badgers, it seems. We don't have to think about how to recognize a cat or a dog. Our brains, we see when our brains automatically have learned the patterns with neural networks, and we instantly know that this is a cat or a dog. We don't have to look through a book of pictures and say which one is this closest to. And so with a computer, we can train a network to do this. We take the data, here are a lot of different images of animals, you train the network, and then you can deploy it almost instantaneously to identify a particular image, here a dog. If you go to the next slide, without going into the details, this just shows this actually working. This is a small animation of the tool that was using. We had a graduate student, Daniel George in Illinois, who used LIGO data to train a network using templates of black holes. And this is just an animation showing how it can very quickly, in a millisecond or so, pick out a black hole collision event in the LIGO data. And so these tools, these modeling, these new data approaches open the door to being the era of multi-messenger astronomy and being able to really take advantage of all these instruments that are going up. With that, I'll pass it on to Miguel to go even further into the future.
Okay, thanks, Gab. Well, I first just want to say that I met Gabriel Allen in 1991, so 30 years ago, and I met Ed Seidel only a couple of years later. So we've been working together for quite a while. And during the time I was doing my PhD in Cardiff, we were working on these things that I just talked about, numerical relativity and codes to collide black holes and things like that. But we also had a nice tradition. So all the group of PhD students would usually once a week get together to watch Star Trek. So we watched several episodes of Star Trek all the time. And doing that, once I had an idea, which is what I'm going to talk about now. So you probably heard that nothing can travel faster than light. That's one of the first things you learn when you learn relativity. It violates causality. The speed of light is the top limit. But of course, you watch Star Trek and they go zooming around the galaxy faster than light all the time. And they use something they call the warp drive, which nobody knows what it means because it's just science fiction. It's just a nice word saying they do something to space and they travel fast. Okay, so that's in science fiction. That's just a catchphrase. But once I was watching one of these episodes, I don't even remember which one, and I started thinking about that. So one of the problems with traveling faster than light is that you do it on a fixed space. But Einstein also taught us that you can change the geometry of space. You can curve space. That's the concept of general relativity. That's where gravitational waves and black holes come from. And there's one particular aspect of GR that tells you that space expands. We know from the 1920s that space is expanding. Galaxies are moving away from each other. And they're not moving away from each other because they're actually just moving through space. It's actually they're sort of sitting where they are, and space between them is expanding. It's getting larger and larger. So that's an idea that I always had in my mind. And you know also that galaxies move further away from each other faster if they're farther away. So a galaxy that's close by moves away from us not very fast, but if it's twice as distant, then it moves twice as fast. So the expansion of the universe makes galaxies move faster as they're further away from us. And a question people always ask, which is when you give talks about the expansion of the universe, smart people always say, what happens if you go sufficiently far away? Is it possible to have a galaxy that's so far away that it moves away from you faster than the speed of light? And sometimes they say, "Well, this would contradict relativity." Well, the answer is it does happen. Galaxies that are sufficiently far away from us move faster than the speed of light. We call that the horizon, the cosmological horizon. And I know it doesn't violate relativity because nothing is moving faster than light through space. It's space itself, the one that is expanding. So I had this in the back of my mind all the time. And then this time when I was watching Star Trek, then I went home and I said, okay, maybe we could travel faster than light. If we can do it because galaxies sufficiently far away actually move away from us faster than light. If we could do that in a small scale, if we could expand violently space behind myself sufficiently fast, then I would move away from whatever's behind me faster than light. And that shouldn't violate anything. And then I said, well, but that doesn't help me to get where I want to go. If I go to another star system, then moving away from the sun, but not getting closer to another star doesn't help. So what if I do the opposite? What if I contract space in front of me at the same rhythm to which it is expanding behind me? So both effects sort of cancel out, but in the meantime, I'm moving away from whatever's behind me, closer to whatever's in front of me. And I can do it faster than light. And that would violate no laws of physics. But that was the original idea of the warp drive. I actually went next day, it was a Saturday, I remember 7 a.m. I was already in the university doing calculations with an old algebra program called Maxima. Today we have Maple and we have Mathematica, but at the time we had this Maxima code. And I started putting the equations together and feeding them into Einstein's equations to see what happened. And I was surprised that I could actually come up with a geometry that did this exactly what I wanted very quickly. In a matter of a couple of hours, I already had a geometry, an expression for what the geometry of space should be doing, or space and time should be doing, that will allow you to, in principle, do that. But the next question is there any kind of energy and matter that actually produces that kind of geometry? And for that, you need to go back to Einstein's equations, the field equations of general relativity, which Ed actually showed in this presentation. There's equations that relate the curvature of space to the distribution of matter. Normally, when we solve Einstein's equations, we do it the other way around. We do it the hard way around. We say we have a distribution of matter here, say a star or a galaxy or something like that. And we put that into the right-hand side of the equations and we solve for the geometry on the left-hand side. That's actually really hard. And that's what Ed said. Initially, people thought you couldn't do this because the equations are so horribly complicated. And we can actually solve them in a few special cases, but it's a very hard thing to do. But going the other way around is extremely easy. You just say, I like this geometry. For some strange reason, it's an interesting geometry. I plug it into Einstein's equations, and essentially I just read off what is the matter content. So when you do it this way, it's not actually a true solution because you're sort of cheating. You say, I like this geometry, and then I figure out what sort of matter I need to produce this geometry. But you can always do it and play with it. So I did this, and I discovered something I didn't like, which was that you need negative energy to produce this warp drive geometry, this expansion and contraction in front of you. So in principle, it doesn't actually violate relativity, but you need negative energy. And of course, for people that are not physicists, negative energy doesn't mean a lot. Who cares if it's negative? But if you remember E equals mc squared, negative energy essentially means negative mass. And negative mass should really scare you. We've never seen negative mass in the universe. So it probably doesn't exist. And so that was a disappointment. I needed negative energy. That was bad. So what to do? Nevertheless, I wrote something up, some of the ideas. And I went to my supervisor, Werner Schutz, who was also Gabriel's supervisor. I was a bit scared because I said, he's going to tell me I'm completely crazy and go back to coding and doing black hole collisions. But he didn't. He actually liked the idea. He read it very carefully. He gave me a few pointers, a few corrections. He said, this is really nice, Miguel. I like this idea. You should publish it. At that time, I've never published a scientific paper. It was going to be the first scientific paper I had ever published. So Bernard helped me to sort of get the right format and things like that. And it had a pretty boring title. It just said hyperfast travel in general relativity. And he told me, no, Miguel, that's not going to sell it. You have to put something more interesting. You should call it the warp drive. So I did. I wrote the paper and I called it the warp drive. That was thanks to a suggestion by Bernard Schutz. And that was it. And essentially, I never worked again on that problem because this idea of needing negative energy, I thought it was a serious problem, and I couldn't figure out a way around it. But in the meantime, in the last 25 years, there's been lots and lots of papers of people retaking the idea, studying different aspects of it, trying to reduce the amount of negative energy, trying to see if you can get away with no negative energy. That's something people had tried to do last year. So people had really worked on it. And it's actually at the moment, I think is my most cited paper, which is amazing because it's my first paper. And I never went back to it. But still, it's a nice idea. I mean, I think it teaches you that this fact that you cannot travel faster than light is not just, you need to qualify that. You need to say you cannot travel faster than light through space, but you can in principle deform space, change the geometry of space, that will allow you to travel faster than light if you deform it in the right way. I'm still sort of hopeful that maybe we'll be able to do this sometime in the future, even though it requires at the moment negative energy, because we do know that it actually happens in nature. Galaxies that are very far away from us do move faster than light away from us. So that actually happens. And also, and the other extreme of the universe, at the beginning of the universe, when the expansion of the universe started, in this cosmic inflation, that expanded the universe exponentially during the first fractions of a second, what you need to produce this cosmic inflation also requires a form of negative energy or anti-gravity. And this is sort of part of mainstream physics. So again, maybe if we could learn to control it, this inflation field, or even this negative energy, this dark energy that pervades the universe and is making the universe expand even faster all the time. If we could learn what negative and what dark energy is, and if we could learn how to control dark energy in the lab, maybe we could use it to produce a warp drive. So I'm a bit hopeful. I think all in all, general relativity still has a lot of surprises for us, because now we're used to thinking about black holes, and we've been thinking about black holes for almost 100 years. And now we're thinking about gravitational waves and cosmology. But I think there's going to be things out there that we're going to discover that are going to blow our minds. And they have to do still with general relativity and strange forms of matter and energy that will allow you maybe to do something like the warp drive. So I'm sort of hopeful. But I just wanted to give you the anecdote about how it happened, and also the fact that I have never worked again on that subject. But it's an interesting subject. It's not the only way. I mean, there's previous ways. People have also talked about wormholes, and a wormhole is also a way to travel faster than light. It also requires negative energy, but it's actually, I think, worse than the warp drive, because you need to plug a hole through space, make a hole in space here, and make it come out somewhere else. And we have no idea how to do that. Nobody has any idea how to make a wormhole from scratch and how to make it go where you want to go. So I think that's even worse. But maybe in the future we'll be able to do something like that. But again, just to finish, it's not actually what I do. It's just what I did once. Never gone back to it. What I do is what Ed is talking about. I do numerical codes, I collide black holes, I form black holes, and that's what I really like to do. And that's as a more real astrophysical application, which is also what Gabriel was talking about. We can predict what is happening out there when black holes collide, the gravitational wave signal. When neutron stars collide, maybe we can learn about the equation of state of nuclear matter, and that's actually more down to earth, even if it's about black holes and neutron stars, but it's more down to earth astrophysics. True astrophysics, which is what I do most of the time. But anyway, I just wanted to talk about a little bit about what maybe the future can have for us.
That was great.
Yeah.
That was wonderful. Thanks so much. Gabby, were you going to say something?
No, I'm just putting my mute off in case.
Oh, okay. Well, if any of the co-stars have any questions for Ed or Gabby or Miguel, feel free to ask them.
Well, I have a question for Miguel, if I can.
Yes.
I was sort of intrigued that Nick also was at Cardiff, where we were, and so we had the Doctor Who, of course, is based there. Sorry, I'm coughing. Yeah. And I thought I remembered that you started looking at the TARDIS as well, and I wonder if you made any progress on the TARDIS metric.
Well, yeah, I never actually pushed it too far, because the TARDIS metric, in simple terms, it's actually part of general relativity. You can find it in many books, even it's not called the TARDIS. So if you know what the TARDIS is this police box that Doctor Who goes into, and it's much bigger on the inside. Actually, on the inside it's a huge palace that has everything, and on the outside it's just a small police box. And the geometry to produce a space that is bigger on the inside than on the outside, it's been known for a long time. Usually you do it in spherical symmetry because as the joke says, even Sheldon in the Big Bang Theory would joke about this, physicists always think about spherical cows. So you do it in spherical symmetry. And in spherical symmetry, it's actually called a bag of gold. A bag of gold geometry is a geometry that's bigger on the inside than on the outside. It's called a bag of gold precisely because you have something that's big, but it's closed on a throat, right? And you keep your gold inside. But if you do that in a three-dimensional setting and you imagine that you have a small portal and you go through it and inside you have a very big space, then that's called a bag of gold. And you see it even in textbooks. So when I realized that that is essentially the TARDIS geometry, I stopped worrying about it.
But the time travel part of it, though.
The time travel, I have never thought much about time travel. I think, but in order to be able to travel through time, you would need wormholes, but wormholes through time, not through space. Which is, I'm not sure if that's what Doctor Who does, but.
I've actually been curious about the issue of time travel with a warp drive. You know, what would it be like for like the time that you experience traveling way faster than the speed of light relative to a stationary observer?
It's an excellent question, and I don't know the actual answer in physical terms, because when I came up with the geometry for the warp drive, I sort of cheated. I just came up with the geometry I wanted, and to make it simple, I assumed that there would be no time dilation, so that the object that's traveling faster than the speed of light inside this warped up bubble has no time dilation with respect to the outside. But that's by construction. That's the geometry I come up with. Whether that is realistic or not, it's probably not realistic, but I don't know what else would be more realistic, so I don't know how to fix it.
Maybe circling back to what you're working on now, or what's do you have a most interesting, and this might go to all three people, which is most interesting type of black hole? Are you interested in small, large, different types of collisions, spin, no spin?
Yeah, I don't know what Gabriel is doing now, but in my case, I'm not actually colliding black holes because you need supercomputers for that, and at the moment, I'm not working with a supercomputer. So I do simple things on my desktop. I produce black holes from the collapse of strange camps of matter. So I study a lot of boson stars, which is something Edsel actually did a long time ago, and I also study things like different kinds of fields that produce black holes, and how they collapse and form a black hole, or if they can be stable objects. So I'm doing a lot of that recently. They're not actually very astrophysical as far as we know, but they're interesting. So I always like the interesting side of GR, even if it's not directly applied to astrophysics.
I so hope for boson stars. I've got my fingers crossed. That used to be my Sunday project. I didn't want to, because it was so weird at the time, just like only work on that on Sundays, but that was the most fun. But now, there are a lot of papers about boson stars, and now that everybody knows how to do black holes, it's gotten less interesting. I'd rather do the weirder stuff.
Yeah, exactly.
Yeah, say more about that for the folks who don't know. What the heck is a boson, and what is the boson star?
I'm going to let Ed do that because he's the one that started this.
Yeah, it turns out there is a solution to Einstein's equations of a complex self-gravitating scalar field. So that's it's a mouthful, but basically it's like there's an internal oscillation in this field. So the real and the imaginary part of this so-called scalar field kind of oscillate in exactly the opposite way, in a way to keep, there's a space-time energy there, but there's a static solution. So there's sort of this bosons that sort of, another way of looking at it is that these bosons collapse down, and it turns out that there's nothing to stop them from keep collapsing down until they get really in the same state, near each other. And then because the Heisenberg uncertainty principle says that particles that are bosons by the uncertainty principle then will have to be pushed out. So it's basically Heisenberg uncertainty principle that says that there's a sort of a pressure that keeps them apart. And so the thing is, are there such particles in the world? So anyway, I spent a lot of my time on Sundays trying to simulate what would happen if you had bosons and then they collapsed and formed boson stars, and could they ever be observed and so on. And one of the things that kept me going on it was that Kip Thorne would always ask, so what's going on in the world of boson stars? Because he always wanted to know something a little bit, different from the standard things. And so these days now, the people are talking a lot about them. They could be a candidate for gravitational waves. Now we discovered that would be really exciting.
Yeah, also boson stars are being thought now as modeling the galactic halos. Extremely lightweight bosons could produce boson stars the size of galaxies. And then maybe the galactic halo is that, and maybe dark matter is actually a boson star, right? So, or a boson field. So
yeah, so like the Higgs particle has been discovered, right? So it's a boson. And so there could be other sort of light scalar particles that people are talking about, axions and lots of things that could be candidates for to form boson stars.
Very, very cool. Thanks for that. Any other questions from anybody?
I have a question. I want to ask Lauren. I worked a lot when I was at NSF on getting the LSST, now the Vera Rubin Observatory, going. And I was so privileged to go down there for the first stone to be laid. And anyway, I want to know how close is it to being operational?
Yeah, good question. We're getting much closer. Our schedule's been delayed a little bit because of the global pandemic. We're still in construction, and so that's pushed us out. But operations is set to start in 2024. So really not that far away considering how long it's taken us to get here. But there's been some big advancements recently. The dome is all enclosed now. The whole telescope mount is assembled. The camera is pretty close to complete. So it's just getting to the point of getting all the pieces in Chile and integrating them all together and getting it working as a system. So the hardest part, really, when you think about it, making all those really complicated pieces work together, but it's getting really close. It's exciting.
I hope you've had a chance to talk about it on this podcast. It's the most exciting optical astronomy project. I mean, or any astronomy project to me, I would say these days. Making a movie of the universe, fabulous.
Yeah, I was showing off. The dome is moving, the telescope mount is moving, so we're very proud.
I do have one question, if I may. What drove you all, and maybe this is kind of opening a can of worms here, but what drove you all to pursue this particular field to begin with? And I say this, I asked this question coming from a completely different perspective. I flew jets in the Air Force, and now I'm a physician, and so medical doctor. So I have zero background in the stuff that you all study, but I find it fascinating. And so I'm just curious, how would somebody come around to, pursuing a field like yours? And how did you do it?
I'll give a quick answer, let the others go too. But I was a kid in the 60s, and I watched Star Trek, the original series, as it was, when it was kind of real time in a sense every week, and it was my favorite thing. But so that really influenced me, as did the space program itself. And then you started hearing about black holes around that time. At that time, it's thought of as like a crazy concoction of the physicists, the astronomers. Even when I was in graduate school, astronomers basically didn't believe in black holes very much. Most of them thought it was like a crazy idea of the physicists. But I just always thought it would be so amazing to be able to work on it. And I never thought I'd really be able to get a job doing it. But somehow I actually did. So it was fabulous.
For me, it was a lot of luck, I think, having the opportunity to keep moving forward. But originally, I took a course in differential geometry. I did a math degree, and I really thought differential geometry was very cool. And then the fact that you could use that in relativity, that's why I took the general relativity course.
Yeah. In my case, it's very similar to what Ed said. I mean, I grew up in the 70s and also watching Star Trek and reading science fiction. I mean, the first books I read because I wanted to read them, not because they asked me to read them at school, were Isaac Asimov's novels of Foundation and Galactic Civilizations and things like that. So thinking about space always fascinated me. Initially, I wanted to be an astronomer. That was my first goal. And I started physics thinking about becoming an astronomer. But then during the physics, I discovered general relativity and black holes, and everything is just geometry. And as Gab was saying, also differential geometry. And I actually fell in love with that, with the math and with the physical concepts, and I just kept going that way. And I also started, the other thing is I started writing computer code when I was very young. I was 14 when the first computer arrived at my school. It was a very old computer with 4 kilobytes of memory, And I started writing code in BASIC when I was 14, and I fell in love with coding. And eventually I found a way in which I could combine computer codes with relativity. So that was it.
Awesome. Thank you.
I think several times the topic has come up of how science fiction has inspired science to reach beyond what's possible at any current time throughout history. And I always think of like Jules Verne, talking about like going down to the bottom of the ocean or like flying to the moon, and how that was so absurd just over 150 years ago. And I love that there's still modern day science fiction that's pushing the envelope and getting people to think about what's possible and what the future might hold. So yeah, I think it's pretty terrific. And there's there's precedent of science fiction becoming science, which is even more exciting.
Yeah.
Any other thoughts, questions, excitements?
Well, I make another comment just about the evolution of the field. So it was really true that some of the most brilliant people in relativity worked for decades around the world to try to find ways to solve Einstein's equations. And I spent, in fact, I would say, I spent almost all of my career failing to be able to simulate two black holes. Any student, undergraduate student, in fact, you can just download that code that Gab was talking about, and anyone can do it. It's like child's play now. So it's an amazing advance in the history of a very interesting field, and it's a wonderful future that comes out of that then, because the tools are there, and now a lot of the physics can finally start coming out of it.
Yeah, with the advances of technology and the new telescopes that are coming online, like the one Lauren and Nick are working on, I think the discoveries we're going to make in the next decade or two are going to potentially change our understanding of the universe, just like Einstein did 100 years ago.
For sure.
Yeah, I think we're just, as a comment, we've learned so much about the universe in the last 100 years. I mean, 100 years ago, people thought the Milky Way was all there was. Nobody thought there was anything outside the Milky Way. Now we have billions and billions of galaxies, and we can see it from the beginning of the universe. And just in the last 20 years, I mean, we've discovered that the universe is expanding faster. It's not slower. That's only 20 years ago. We discovered gravitational waves. We took a picture of a black hole. Very exciting things are happening in cosmology and astronomy in the last few years. And I think we're entering a golden age when we have now technology and satellites and telescopes that we couldn't even dream of a few years ago that will teach us a lot more about the universe. I mean, I'm impressed. When I was studying physics in the 80s and you took a cosmology course, they would tell you the universe is somewhere between 10 and 20 billion years old. Today, they tell you it's 13.8 billion years old. It's amazing how it's changed, right?
We just got a really interesting question from somebody watching. So Phil Round says, I have so much respect for scientists and the scientific method. I wonder how folks cope with the lay society that is becoming more and more distrustful of science in general.
Well, I'm sure we all have comment on this. I find it extremely disturbing. And it's also, there's a certain, it's almost a paradox. How could we advance so much in science? Like compared to the 50s, let's say, I've really thought a lot about this. In the 50s, science was often portrayed and seen, I think, obviously genuinely as a solution to many of society's problems. And you see this particularly like around vaccines, for example, the Salk vaccine and for polio and so on. So it was really seen as a great tool to advance society. Now science has advanced so incredibly in the last 70 years, and yet it's become so politicized and become very distrusted. And I really find it disturbing. And one of the causes of it, and there are many causes in society, by the way, this is another good example why the social sciences need to be funded much more, because our biggest problems are in social science and they cost so little compared to the a telescope or a gravitational wave detector. But anyway, it's a sort of a side comment, but I think an important one. But the thing is that back in the early 90s, I was at the University of Illinois when the web browser was invented, the graphical web browser at NCSA. Mark Andreessen and Eric Bina, among others, Ping Fu, and there's a little team there that unleashed that whole revolution. And no one that I can recall for years thought about it as a tool to pass misinformation around. And so it has become like one of the sort of most famous and disturbing unintended consequences of a technological advance. We just thought about all the democratization of knowledge and all of that, and how you'd be able to advance society so much. So I think that's one of the reasons, but there are of course many aspects to this.
Yeah, it's incredibly worrying. I'm also very worried about that. I think we need to teach more science in schools for very small little kids, but not just teach them what are the planets and things like that, but teaching how do we think. That science is a way of thinking. It's not so much just a bunch of data. It's a way of thinking, as Carl would say. It's a way of looking at nature and thinking rationally and making experiments to check that what you thought was correct. And that's it. There's no mystery. So when people say they don't believe in science, it's really difficult to understand what is it they don't believe in, because we don't come up with ideas just out of nowhere. We do experiments, we check that things are right, and we just think logically. That's essentially all there is to it. So, and I'm worried that people don't know this, and we haven't been able to teach them in school properly. So that's one of the reasons I think that science communication, things like what we're doing now, and television and radio and articles, and science communication is really important. We should really invest in science communication, taking the science to the public, and we should really train a lot of people to do science communication. And we should really also convince scientists, because a lot of scientists think that science communication is a waste of time. And I think that's completely wrong. We really should convince scientists that science communication, taking the science to the public, is very important, particularly from what we're seeing now, right?
Just to echo all of that, I mean, I think though that people who don't necessarily believe in science, I mean, they're kind of not doing it on purpose, right? I mean, they're the ones that are getting hurt with if they're not vaccinated and so on now. So I think it's up to us to do more to invest in schools and in education. And I know the three of us are professors, so I think it's also a confusing time for people when we were at university. You didn't have all of this social media, you didn't have all of the sort of fake news around the web, or you didn't have to understand what things to trust or not, because you basically could trust everything you were given because everything was coming from a reliable source. So I think we have to change the kind of education that we do to give people from very early on the skills to understand where their information is coming from, and just prioritize funding of education. I have to say, I didn't understand. I moved to America as basically as a professor in 2003. I didn't understand the tuition system here. I didn't realize that you had to pay for education coming from the UK, because I'd never had to pay anything for it before. I had a degree, a master's at Cambridge and a PhD, and sort of didn't realize there was this thing called tuition somehow that you had to find, and that you had to take out a bank loan to go to university and get that education.
I'm 16 months away from being school debt free.
Good luck.
Almost there.
Yeah.
Yeah, I was used to, they paid from I remember, I mean, we were paid a stipend to go to university. I mean, there was a very small number of people that went from my school to university, but you actually didn't have any student debt. I mean, it's different again now there, but I think it's just the overall prioritization of education.
Yeah, I think you all nailed it. I think it's really about having more organizations like Wyoming Stargazing who are dedicated to teaching people about one aspect of science or about science in general, and what kind of questions we can ask and learn from, and how we think about the universe, and how we're all connected together because of that understanding. I think that's a really hopeful way to think, actually, about how everything in the universe is connected. And so that's one of our goals, to help people understand their intimate connections, not just with each other on this planet, but with every star everywhere in the universe.
Yeah.
Lauren, it looked like you were going to say something.
Oh yeah, just to maybe add some more context in that I 100% am on board with education. I'm here. I love doing this kind of thing. But to think about like, why are people distrustful? Like what fear and what like other things are influencing them besides just what they know? Because a lot of times people are going out, they're doing research, they're asking questions, they're just getting the wrong sort of information and they're placing their trust in the wrong places. And so like, why is that happening? And how can we as scientists think about like, what is causing this sort of fear or how people are behaving the way they're behaving? And is there a way that we can change how we're communicating or addressing those underlying like human issues in addition to here is why and how we know the things that we know? So.
And I think we're pretty entertaining.
Yeah, for sure.
I think that just to piggyback off of what you were saying, Lauren, I think, you know, in medicine, it's become, as I'm sure everybody on this call is aware, it's become a really big problem where there's a lot of misinformation, not just surrounding the global pandemic, but just in general. You know, I think originally WebMD, to Dr. Seidel's point, you know, WebMD was a fabulous resource, and then folks started to kind of abuse it and to use Dr. Google as, you know, the ultimate resource instead of you know, thinking that it was infallible, you know, instead of you know, seeking out you know, an opinion or an interpretation from somebody who's got a lot more training. So it's definitely on the medical side, it certainly has been challenging, but you know, I'm hopeful that we can figure out a way collectively as a society to kind of, you know, kind of gather our thoughts and to reattack in a, you know, in a more effective way to make it clear that science can be trusted, you know, and just like Miguel was saying, you know, that it really is founded on discovery, you know, and on testing and logic and all of those things. So anyway.
Well, and it's self-correcting, which is another thing. Of course, like you, I think, Daniel, you were saying earlier that, you know, half of what we're learning may be wrong, but the point is there's always a drive to get to the truth of and to throw away things that are wrong and to replace them with things we know are right, at least we can verify. And I think that just basic scientific method is in these days quite often misunderstood. So you hear sort of celebration almost, oh, the scientists were proven wrong, you know, and particularly around coronavirus and vaccines and so on. When, oh, you're supposed to wear a mask, or masks, you shouldn't wear masks, and then, oh, you should wear, oh, the scientists don't know what they're doing. But it's an investigation, and you learn more and more each time, and you refine and correct, and that's an important part of the whole system. You have to communicate that more.
Yeah, so true.
I've even heard that scientists are the ones, not the ones who should be commenting on the quality of science because they're biased, because they favor science. I mean, literally, that's like an absurd argument, obviously. But so it's something I think about a lot. You know, as the president of a university in a rural state, there's a lot of education, and I very much want to make sure that the university is seen as a source of good information and scientific and trusted information. We're working hard to do that. So, for example, we had a series of videos on the science of coronavirus and the vaccine, how the vaccine works, what masks do, and so on. And we decided to have that all done by our own faculty because they're known in the state, and I hope that they're more trusted than somebody comes out of the CDC, even though they might know more. But anyway, they're local people talking about the science. And so we have to do a lot better to communicate the importance of science.
Well, I think that's a really cool idea and definitely moving in the right direction. We are just about out of time. So I want to thank our three special guests for being here this evening. It has been a lot of fun to have all three of you here with us this evening. So thank you so much for being here, giving up some time in your, I know, a very, very busy schedule. So thank you so much for joining us on the Cosmos Show. Thanks as always to our co-stars, to our streaming master, Gavin, and everybody else behind the scenes who makes the Cosmos Show possible, especially all of you who are watching at home. We wouldn't be here without you. So thanks so much for joining us. And we hope to see you next time in a couple weeks. So until then, be well. And don't forget to look up. We'll see you next time. Bye.
Bye.
Bye-bye.
you.